Main results of the British Antarctic expedition under my command are as follows. We reached a point within 97 geographical miles of the South Pole. The only thing that stopped us from reaching the actual point was the lack of 50 pounds of food.
On the first day of the year 1908, Ernest Shackleton was embarking on his second adventure to the South Pole. Shackleton had great ambitions, from scientific discoveries to being the first person to reach the South Pole. However, finding himself in the harsh Antarctic environment and with supplies running dangerously low, he decided the goal was not going to be accomplished then. He would have run out of resources, and this would have been deadly for both the crew and the hope of making great discoveries in the future.
I'm Hanna Siemaszko, and you're listening to Resourceful, a podcast which explores the exciting new opportunities of space resources. Resourceful is produced by ESRIC in collaboration with SciLux.
Curiosity is the fuel for exploration, and since the beginning of the 20th century, it has taken us further than ever before, proving extreme human perseverance and endurance. No wonder these words are best to name some of the most famous missions or rovers that have been designed for extreme exploration endeavors. Exploring harsh regions of the Earth is indeed a dangerous and tedious activity, requiring long preparation times, years of research, raising funds, gaining public support, and having the right team. What if we want to aim further? Into space? Since the 60s, when we finally had humans traveling outside our home planet, the scientific community and society at large have undergone incredible changes. One red line remains unaltered. The desire to be first to discover blends with the push to know what is beyond. We're also driven by the need to find innovative solutions to challenges that seem unsolvable. We have asked Katherine Joy, Professor of Earth Sciences at the University of Manchester, to share her experience as a planetary scientist, a space enthusiast, and someone who has been to one of the most remote places in the world to conduct science. In 2019, Katherine brought together her two passions, Earth and planetary sciences, and just like Shackleton, embarked on an expedition to Antarctica.
There's a lot to do, but you have to be patient. And then eventually you get the message to say, your time has come, you're going tomorrow at 4 a.m. And so you spend the whole night kind of going, oh my goodness, this is actually going to happen. And sometimes it happens and you go, and other times you sit there and the plane gets cancelled and then you wait a bit more. With spaceflight, I guess the parallel is still that potential delay in launch. So, sometimes space launches, the crew can go to the pad, they can sit there, they can get all the way down to 2 minutes before launch, and the launch will be called off. They'll repeat the same thing the next day, maybe the next day, and then maybe the mission will be delayed 1 month or 2 months.
We can find numerous parallels between exploring Antarctica and space. They are both rather inhospitable places for humans and machines, and they are both fascinating for science, telling us more about our origins. Oftentimes, testing of technologies and human resistance in space analogues is done in the Antarctic. But they are also fundamentally different, with the most impactful differences being the lack of atmosphere in space and hence the lack of air. To reach Antarctica or the Moon, we require fuel. Extreme environments demand protection, be it from the harsh cold winds or from the solar ones. We need to be able to refuel as well as protect ourselves and our supporting equipment using the resources we find in situ, that is, living off the land. All these activities have so far only made use of Earth's resources. When going to Antarctica, we need to bring everything with us. For each rocket we send in space, 90% of it is just fuel. Imagine if for each trip you took, you would have to carry all your gasoline and all your air. Could we then tap into space? What can we learn from our experiences in extreme environments such as Antarctica? How could we explore the universe in more depth and more sustainably? Will we be able to harness the resources we find?
Space resources means different things to different people, and it depends on which planetary surface you are also talking about. There are types of resources which maybe have economic implications, but also have uses in the space exploration sector. And these would be more around things such as access to oxygen or access to water, which could be used to create oxygen to make breathable habitats on future crewed exploration efforts, or water that could be reprocessed into for habitat use, either oxygen to breathe or water to drink, or that could have a use in splitting that water to generate rocket fuel.
When we sent our first lunar missions, they were mostly motivated by political interest. During the Cold War, the primary objective was to demonstrate superior capabilities and technological advancements. The space race of the 60s was all about flexing your muscles. With people eager to witness the new space accomplishments, including the first human in orbit and first steps on the moon, space exploration has truly inspired the public and captured their imagination. Now, 50 years later, its political aspect cannot be disregarded, but the space programs are equally about the readiness of the technologies and materials. The resurgence of interest is closely tied with more nations being capable of sending their landers or probes, as well as increased involvement of commercial actors. At this moment, we are witnessing the development of the Artemis program, a collaboration between NASA, ESA, the Canadian Space Agency and JAXA, as well as the Chinese program, but also other countries that focus more on mapping the lunar terrain. Additionally, there is a plan to launch a follow-up to the International Space Station, a station called Lunar Gateway, which would orbit the moon. Looking ahead, we can anticipate the emergence of private space stations, lunar tourism, and enterprises involved in extracting space resources.
The moon is incredibly interesting because the Earth and the moon have been sister planets throughout space and time, and so we can look to the moon to ask questions about our own planet's past.
Only a handful of people have so far witnessed the pristine lunar environment with their own eyes. Here is the reaction of Neil Armstrong, who in 1969 was the first man to step on the lunar surface.
I'd say the color of the local surface is very comparable to that we observe from orbit at this sun angle, about 10 degrees sun angle or that nature. It's pretty much without color. It's gray, and it's very white, chalky gray as you look into the zero phase line, and it's considerably darker gray, more like a ashen gray as you look out 90 degrees to the sun. Some of the surface rocks enclosed here that have been fractured or disturbed by the rocket engine plume are coated with this light gray on the outside, but where they've been broken, they display a very dark gray interior, and it looks like it could be country basalt.
Apollo 11 was a really big test case. Prior to that mission, there'd been a series of orbital missions, so the lunar orbiters that were NASA's mapping missions of the lunar surface, where scientists used that data to undertake the first geological mapping activities. So we knew that there were dark areas on the moon. We knew that there were light areas on the moon. We'd had some landers that had tested the nature of the lunar surface. They'd actually landed to see, was it made of powder? Was an astronaut going to step out of the spacecraft and disappear up to their neck in loose powder, or was it made of rock?
Houston, Tranquility Base here. The Eagle has landed.
So when Apollo 11 landed, it landed in a really safe part of the moon. It landed at a flat landing site that was thought to have been made by a volcanic lava flow. The rocks were sampled. They got brought back to Earth. And within just a few days, actually, this is what's really cool, scientists had their hands on those rock samples and were running them through their machines to work out what their chemistry was, what their mineralogy was. And a group of scientists were able to measure the first age. And that age turned out to be 3.8 billion years old, which sounds incredibly old compared with the Earth, because most of our rocks on Earth are really young. We're talking like millions of years rather than billions.
According to one hypothesis, the Moon was created as a result of an impact of the body the size of Mars on Earth. It shares certain similarities with our planet, but it also has quite a few particularities. Valuable insights have been gained from samples collected during the Apollo missions, robotic missions, and lunar asteroids on Earth. But some of our hypotheses still need to be confirmed. The first one are the large deposits of ice on the Moon's surface. We do know the ice is there, however, we do not know the exact quantities, and recently scientists confirmed that there may be less water ice than we originally thought. It is an important question because, as mentioned by Katherine earlier, from ice we can obtain water and extract oxygen and hydrogen, essential to produce propellant to sustain longer and deeper journeys into space. Lunar ice apart, there's another resource that deserves our attention: regolith.
So the lunar regolith is the name given to the soil that covers the entire Moon's surface. So the Moon's surface isn't just, rock outcrops like we maybe see in places here on Earth. Those rocks have been hit by impacting asteroids and comets through time, which have pummeled into the surface, pulverized that rock, and turned it into a dusty-like material. In some places, that dusty regolith depth is quite thin. It's on the scale of meters, and then you've got rock underneath. And in other places, that dusty layer is very thick, kilometers thick. So it depends on the age of the surface as to how thick that regolith layer is. It also depends on the underlying rock type as to what that regolith is made from. So the regolith, it will basically be made up of the rocks that are underneath. So if you go to a place where there was once lava flows, the regolith sitting on top of those lava flows will be made of pummeled bits of those lava flows. The regolith is highly diverse and it's an amazing resource. So every soil sample you pick up from the Moon is different. It's got different rock fragments in, it's got different types of components in it, different chemistry. About 40 to 50% of the minerals in the regolith is made up of oxygen. Oxygen binds with other elements like SiO2, silica dioxide. If we can split those compounds and get the silica and separate it from the oxygen, we can again use that oxygen for other applications, be it in moon bases to breathe, be it in rocket fuel use. So the regolith itself is wonderful because it could have all these other uses as well. If there are missions that are sent to test questions about resource abundance, certainly there are specific places that we would want to go to, either to do with the polar areas where there may be ice deposits or to visit places where we have enhanced volatile abundances elsewhere. That type of resource scouting has not really been done so far.
Once we establish the exact locations and concentrations of resources, there is a need to develop numerous technologies that will work seamlessly and in low gravity. We will be forced to design autonomous mobility solutions or factor in the delay in communication. The other challenge is miniaturization. As mentioned in the introduction, each kilogram of material that needs to be brought with us is extremely costly and takes up space that could be used for transporting other crucial tools or supplies. The future of space exploration is about close collaboration between robots and humans. But first, we need to start with cooperation of organizations and countries on Earth. Just like in the case of Antarctica, the story of space exploration is a story of teamwork and international collaboration. With the Artemis Accords, Lunar Gateway, and national legislation on in-situ use of space resources from countries like the USA, Japan, Luxembourg, and United Arab Emirates, we can see the appetite in many organizations to go the extra space mile.
I think that some organizations and some countries are taking it incredibly seriously. I think that there are companies that see the potential profitability, particularly in terms of harvesting regolith material for rocket fuel, for example. If you can be producing rocket fuel, you can sell that fuel to rocket suppliers that may want to launch vehicles off the moon to go elsewhere in the solar system. So I think there is an economic argument to be made, but it does hinge on this fundamental question: what reserves are there? Are the concentrations of material really enough to do this in a sustainable, and by sustainable I mean, can we keep on doing it over and over again, and potentially for those companies a profitable way? And that's the big gap that I think, another big gap, there's lots of gaps in our knowledge that has to be thought through. And I guess this is going to be incredibly risky for the first venture capitalist companies that want to do this. I guess we can look for parallels back to things like the gold rush, thinking about people taking huge financial risks for potentially huge financial gains, and the types of companies that are willing to back those people and financially support them. So I think there's a lot of big risk factor involved. And I imagine when we know a little bit more about the moon's resources and where they are and what concentrations they're in, the next step will be companies really coming on board and thinking about how to make these into commercial ventures. Science has the great potential to gain through commercial operations. So we wouldn't know nearly as much as we know about the Earth if it hadn't been for mining companies and it hadn't been for oil producing companies who collect samples to make them available for scientific study to understand how those resources are there in the first place. I can foresee the same thing, hopefully, being true with the moon. Commercial companies will want scientists to validate their results, and presumably scientists will benefit from access to samples to do interesting things with, to learn about the moon and solar system. Conversations are important, and we shouldn't stifle the views of one sector of the community or the other, but should try and come together to find ways of thinking about how we can set the framework for doing this in a way we think benefits science and benefits the sustainable environmental impacts on planetary surfaces.
Occasionally, the media discusses space resources in the context of possible rare earth material presence and bringing them back to Earth. The feasibility of such operations is rather questionable at this stage. In the short term, we should focus on obtaining the resources for space use. The so-called ESRIC, or in-situ resource utilization, should let us make substantial savings on sending materials to space, both from the cost and energy perspective. However, first we need to investigate having the right technology and the right approach to exploiting the resources we find. We need to remember that if we do decide to extract them, we will change the surface forever. Could it be that space exploration is where we implement better environmental policies than on Earth? And how can we choose the most responsible way and follow it together?
I mean, the technological challenges are immense, I think. On top of the environmental concerns, the how do we change surfaces of planets that could have a change that lasts for millions, if not billions of years? And how can we plan for that in a way that we, again, learn the lessons that we've learned here on Earth?
This is the future, but for now we are focusing on getting a crewed mission back to the moon. First steps have been taken. Artemis 1 mission has been completed and we are now eagerly waiting for the next ones. In parallel, China is also developing its own program, which has equally ambitious goals. Undoubtedly, the projects are fueled by commercial partners that have never been as present in space exploration as they are now. If the missions can confirm abundance of certain elements on the moon and then on other celestial bodies, huge investments into space economy will follow. No decision regarding a lunar mission is trivial. Take, for example, choosing the right landing site.
The Artemis program, which is a NASA-led program to get back to the moon, which involves collaboration with the European Space Agency, the Canadian Space Agency, the Japanese Space Agency. This is, a multilateral venture. Artemis will go back to the moon. It's already started the test campaign to build the large rockets to do this as Artemis 1 has happened. We've tested the rocket. Artemis 2, which is launching a crew on a big rocket to go around the moon, is supposed to happen next year. And then Artemis 3 is currently scheduled for December 2025, when we'll send crew back to the moon's surface. So to do Artemis 3, some of the decisions have already been made. We're going to go to a South Polar site. What's not been decided yet is which particular site. So there's 13 possible candidate sites. And over the next couple of years, that will be planned down to a short list of, a few, and then eventually 1 or 2 landing sites will be picked. And the reason you need a couple of landing sites with Artemis is because it's a polar mission. It's different to what we did with Apollo, which was all in the equator. Down near the poles, there's a lot of shadows compared with the equator. It's very dark. And so depending on when you launch that mission, some of the landing sites may be in darkness or have very bad lighting, and other landing sites may be a bit better.
The integration of in-situ use of space resources has the potential to completely revolutionize the way space exploration is being conducted. In the long term, it can decrease the cost associated with space flights. It can make our activities in space cleaner and bring circularity into the space equation.
I think that probably like the other areas of science, sustainability is something that's become a lot more aware over the last 5 to 10 years or so. Certainly, I don't remember conversations connected with space missions and designing space architectures to think about how we do this sustainably, to think about, what happens to the spacecraft after we've finished using it, or if we go to another planet's surface, how are we modifying that surface in a way where we could be leaving a permanent scar or a permanent mark, or littering it with the space debris that we leave behind or crash into the surface. So I think there has been awareness, but certainly in terms of thinking about how there is legislation to deal with some of these things, we're really only starting on that journey at the moment. And I think there is a lot of awareness, perhaps driven by people's perceptions around climate change and environmental damage that we see here on Earth from mining operations and waste products from the geological sector, that we're now starting to ask those questions, to think, well, if we want to do similar types of processes, access resources in space, are we going to learn from the mistakes we've made on Earth? Are we going to learn from the cultural perceptions that come with us exploring new environments for resource access here on Earth? So those conversations are, I think, welcome. I think they're being openly discussed, certainly within the scientific community.
Be part of the conversation. If you enjoyed the episode, share it with your friends and subscribe to our channel. If you want to find out more, follow us on social media and join our annual Space Resources Week conference. Until the next episode, stay curious.
This series is brought to you by the European Space Resources Innovation Centre, ESRIC, supported by the Luxembourg National Research Fund, FNR. It is produced in collaboration with SciLux.